This is the new kid on the block. It does things with laser. Everybody likes lasers. I like animations. So you got these little vibration modes on a water molecule. Well, that's exactly what happens in this laser system. If you bombard a particular molecule with the right wavelength of a laser, it starts to vibrate and move around and rotate and things. And so this is the infrared absorption spectra of this particular CO2 molecule. And you see there's lots of bands, and it's pretty complicated. Wait, it gets better. What if you want to look at other isotopologues of CO2? Now we've got C12, C13, O18, and all these bands. Well, it turns out that these lasers don't really scan very far. So you have to be clever here and choose some part of the spectra where they all overlap so that you can get all those isotopologues at the same time. And that's what these guys do. Okay? And here's how they do it. You start off with a chamber with a laser and some mirrors so you can bounce this light around. And what you do is you send the laser through, and you've got a detector, and you get this chamber filled with light, and then you turn the laser off. Some of the light leaks out, and it starts to decay down to 0. And you measure, how long does that take? Then go ahead and put something in that chamber that absorbs. And you do the same thing, but now it decays faster because some of that energy has been absorbed. And the difference in time from here to here is how they calculate isotopes. And if you choose the right wavelength, you can get all those individual isotopes. You buy these instruments for specific gases, whether it be methane, CO2, whatever. And the lab that's running waters right now is using this system upstairs. Okay, this is where the handout kind of comes into play, but you can just use it for reference. A little case study, and I was part of this. We got a lab decided they wanted to do what I call designer reference materials. So they grew a couple of different plants hydroponically. What they were doing was adjusting the nitrogen in the water so the plant would have a different nitrogen signature. They sent, it's called a round robin, they sent these materials out to these labs, and we all analyzed them, and we sent the results back. So there were 8 labs, and you can see the data. So I want you to remember these graphs, because we're going to talk about these graphs as we go through, because there's some problems on these graphs. I'm going to explain to you where those problems come from. Now, I think tomorrow and Thursday, or Thursday and Friday, Renee Brooks is coming here, and she's from the EPA, and she's going to spend a lot of time talking about quality assurance of isotope numbers and doing corrections and things like this. But I need to introduce quality assurance, but that's about all this is going to be. She'll deal with most of it. But labs like this one here have a plan to make sure the numbers come out properly. This is a traditional plan that most people use. I'm going to use a slightly different model for the next couple of slides, that I've added another component over here, which I call a quality assessment. But what I'm going to talk about applies to no matter what title you put to these things. So we go by a principle of where we treat everybody the same way. All our samples are treated identically. And this term of identical treatment came about from who Keith and those guys did that years ago. But Brian Fry and Carter decided they needed to have a little more information about that. So he broke it down into even more kinds of principles that one should do if you're doing isotope analysis. You know, for instance, let's correct everybody the same way. Let's use the proper reference materials, and let's do normalization properly. Let's make sure that when we do error detections, everybody's treated the same way. But we can't talk about all those, so we're just going to talk about this portion right here. And this is important for you guys, and there's one sentence coming up, which if you take nothing else away from this talk, please take that away. So why do we do this? Well, first, it puts us on the scale so that numbers you get in your lab, Todd understands, Seth understands in his lab, Darren understands in his lab. They're all on the same scale. You can correct your data off the instruments. The instruments change every day, so you have to be able to correct things back to some normal, some set of standards. Most labs want to keep a record of how well they do things. Reference materials are what you use to keep a record like that. And if you want to compare with other labs, then you use reference materials to do that. Okay, so take home this message. Your data is only going to be as good as how well you treat your reference materials. If you don't do it right, you won't know what your data means. Okay, so this is important. Okay, so what makes some good reference materials? Well, it needs to be homogeneous, needs to be, nicely, it would be a pure chemical. Something stable that won't change over time. You don't want it to change. If you want to do normalizing, you'd like something that spans. Now, normalizing is just bringing your data onto a known scale. And you guys are all going to do that starting tomorrow during lab. But not everybody understands what this means. So here's an example. So I've put on this graph kind of the normal range for some common materials, C3, C4 plants, and some marine materials. Okay? Properly chosen reference materials would span those materials so that they're on outside of your samples. You get your best corrections if you do that. So you can see this is one we use, these two materials here you can buy from USGS and get them into your lab and use those. They do a pretty good job of spanning everything. But then you can always run into problems like this, where using the same materials, but let's say I was using it natural gas. Well, if I'm analyzing down here, I'm probably okay. But if I'm analyzing up here, maybe these aren't the right choices. So what does that mean to you guys? Here's a lab from California, and this is just a subset of their reference materials that they have on their cabinet. Okay? This is only one page. And if I break it down to waters, look at, they've got like 8 or 9 different waters spanning a whole bunch of isotopic ranges. Every lab. Todd, how many reference materials you got in your lab?
Over 50.
50, and I'll bet every lab in here has got a whole bunch of those things. But in order to do the spanning, you have to have a whole bunch of them. Okay. Quality assessment is a material we use to say, well, how well did we do? When we ran the sample, did we actually get the right number? And quality assessment materials, now here's a couple of examples you can buy from the National Institute of Standards and Technology. One's a ground up peach leaves, one's some animal liver. And this is what they were designed to be used for, looking at trace elements. And when you buy these things, you get a nice little certificate. And on that certificate, there'll be a bunch of numbers for trace elements. And one of the numbers we tend to like is it gives you nitrogen content. That's the number most of you want to see. What's missing from there? It is not certified for stable isotopes. It's not, never was meant for that. So what do? Well, you find your buddies, send them some ground up material and have them analyze it, come up with an average, and say that's exactly how you generate reference materials if you can't purchase them. Okay, normalizing is one of the corrections that we do. And so here's some actual data. For nitrogen and for carbon, we happen to be measuring collagen. Normalizing is simply a linear correction where you take your measured values versus your known and come up with an equation, which you can then apply to your unknown values to bring them back on the line. Does it work? Well, here's some corrected values. Here's the known value. Same down here, corrected and known. Same here. So it does work, and you guys are going to do that for every data set you get. You're going to be doing normalizing. There may be other corrections, blank corrections, other things, but everybody's going to do this one. So back to our little case study at the beginning. This lab here seemed to have a problem. Those were multiple measurements, and it was off by 3 or 4 per mil from everybody else. This was QA key. They had a failure in their quality assurance. This lab down here, well, they didn't do too bad. Number 4, or these labs weren't bad. Number 4 still had a little problem. But the problem with this particular material is not very homogeneous. And here's an example. One of those spanning materials I showed you comes out of our lab in Wyoming. This is those numbers, and here's that number. This is not homogeneous enough to be a reference material. So you have to be very cautious when you select reference materials and make sure that they do what you want them to do. Okay?